On 4.1 problems, we're going to talk about whether something is acidic or basic. And sometimes the answer is neither, because if this is negative, it's not going to attract OH minus. You could say, well, it attracts H plus, but you would be forming a strong acid in water, which cannot happen. You got to know your strong acid and base list, and they think you just know this. It's not that big a list, either one of them, and you need to know it. This is a strong acid. You can't form that. You can write it down on paper. That doesn't make it true. This is not actually going to stick together, and so will it actually become a base or an acid? Nope, neither. This is negative, so it might attract an H plus, so it's a base. C is probably not worth discussing. It's not really going to come up and probably just make confusion. I want to talk about D then. On D, we talked about, I think in the previous lesson, that when you have N with 3 H's, or at least N with 3 covalent bonds, bond, 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 what you have is an unshared pair of valence electrons, and that's a good bonding site for an H. So what you get when we say NH2, and this N is connected to one of these carbons, by the way, what you have is an opportunity for a spot where H plus could attach. So this could be an H plus acceptor, which makes it a base, in which case you get this. And why is it positive? Well, remember, you've added no new electrons, because these just stayed in bonded, and you've added a proton, which is positive. So whereas this was neutral, you've added a positive proton. So overall, at the end, the charge is positive. This is negative, so it could attract an H plus, and you are not forming a strong acid. So will some of these H's really stick? Yeah, some of them will. So it acts as a base. This is not a strong acid, but it does have some H's to give. And so could it give one away? Sure. And then you get this. Here's an NH2 situation again. And again, we have that bonding site there with this unshared pair. So it could act as a H plus acceptor and get you this H3 plus, and so it's a base. Now this one could swing either way because it has an H to give, and yet it could accept one. So which way does it go? Either, depending on the situation, and that's amphiprotic. This has an H to give. This is not a strong base, by the way, a strong acid, excuse me. It's not a strong acid. It is using a halogen here, and I know that is tempting to think of as a strong acid. It is not. However, it could be an acid, just not a strong acid. It will not come all apart 100% when it hits water. But it could be an acid, and if so, if it gives away its H plus, you get that. This is a strong acid, and boy, will these come apart a lot. And so you'll get that when it does it. This has an H to give, in which case you get that, so it's an acid. This is neither. It has no H to give. It's positive, so it's not going to attract an H. And then, though, some kid says, but it will form an KOH, because OH minus would be attracted to it. But you know what you're doing there on paper? You're forming a strong base, and strong bases in water just come apart. So what are your chances of reattaching this? Nothing. Forget it. That's not going to happen, no matter how many times you write it down. So this is neither an acid nor a base, and it won't form that either, by the way. So we said N with 4 covalent bonds, and some of them are H's, especially when all but one or maybe all of them are H's, has an H to give, and we would be running this one backward. Say if you took this one backward, it would act as an acid and form that. So one of these could come off, and then it would have donated an H plus, which means it's being an acid, and you would get that. Could this accept an H plus because it's negative? Yeah, it could. And before somebody shouts, no, it can't, you sit back here, but that is NO3 and this is NO2, and there is a difference. This is not a strong acid. It does not 100% come off in water. The H's do not 100% come off in water. So would some of the H's stick? Yeah, some of them would. I mean, to what extent? Well, we got to go look up the Ka and the K for being an acid, Ka, K acid. Everybody just puts Ka. But some of them will stick. And this one is a bit tricky. I'm glad we've got the answers here. If you say, well, this dissolves, so when it dissolves, you get one of these and two of those, and then what would happen? Well, part of this would certainly be quite basic. OH minus is incredibly good at grabbing up H pluses because you make water out of it. So their point in 2 is that this has an H to give, and yet because it's 2 minus, it's also attractive to H pluses, so it could swing either way. And here it's acting as an acid. It gave away its H plus, and water is the base. Water is the base. This is the conjugate acid. We should have a moment about what's a conjugate acid and a conjugate base. This turned into that. This turns into that. So this is the conjugate acid of water. It is the thing that if it acts like an acid and gives away an H plus, it will turn back into that. So this is the conjugate base of that. If you want to be really picky about it, if this acts as a base and accepts an H plus, you'll get that. This was an acid because it gave away its H plus. There it is. And so it forms this. This is the conjugate base of that, because if it accepts an H plus, it will turn back into that. This is acting as a base because it accepted it, and this is acting as the acid. So this one swings both ways. It's amphiprotic. Now, sometimes you have more than one H that could come off, and so if you take a look at these, here the first H comes off, and the second, then the third. And more importantly, probably, is the idea that this is less and less likely. This is the most likely, then less likely, then even less likely. So the Ka, the likelihood, is rated by the constant K, is getting smaller and smaller. Right, the net ionic equation. Well, if this gives up H to that, you get that, of course. Remember, NH4 positive is an acid, and in the presence of OH minus, yeah, it almost certainly is gonna. This is gonna chew up that until this is all used, well, until one of them is used up anyway, right? We don't know which one is the limiting reactant. It depends on how much we have in this particular solution at this time. But this reaction will happen until one of them is chewed up, and you get, it's making this the whole time. This one, if you give it the presence of H plus from something else, would make, and here's the point, here's the real good point. In general, what you'd get though is not H2CO3, because if with just a little bit rearrangement on C, now it's tempting to say this will make H2CO3 when it attaches, but with just a little rearranging, you get two of nature's very favorite chemicals, water and CO2, and these are really low energy, and they sit around not doing much, and they're very stable and low energy, and nature loves to make them, and we just have it by the just absolute tons. I mean, billions of tons in the case of water, probably. And then some kid says, but water participates in rust, and water does all kinds of things. It's because some kids got really warned about leaving their bikes wet and stuff. But if you need to do it, go on YouTube and look up the equation and the chemistry for rusting. Water is neither created nor destroyed in rusting. It is not part of the reaction of rusting. Water with ions in it to carry electricity, or very low levels, I understand, but to carry electron flow merely acts as a carrier, like I said, for the electrons, and water is not part of the net ionic equation of rusting. Water does not actually do the rusting. It is not a participant. It is neither created nor destroyed. It just sits there, basically. Carbon dioxide just sits there in the atmosphere. That's kind of the problem with this global warming business. And then some kid says, no, it's very useful and it gets used all the time in photosynthesis. Well, yes, it does. If you have a very specialized cell with a lot of evolution behind it, some very specialized chemical in the presence of light, yes, I didn't say it can't be used, but it sits around on its own doing nothing. I know that photosynthetic plankton and plants and so forth are in the business of tearing this up, well, actually both of these, right? And making sugars out of them. But on their own, they sit around not doing much. They're low energy, and nature likes to make both of these. If you give nature the opportunity to make either one, it will, and both is like a bonus. It'll do it. On this, I know that this is liable to form this because, again, if you do the Lewis dot diagram where we talked about it above, this has an unbonded valence pair, which is a good landing site, bonding site for an H plus that's on offer, and that's kind of on offer. So could this happen? Yeah, it could. Now this one could swing both ways. It could accept an H, or maybe it could give one. I'm going to bet it's more likely to accept one. And oh, look here, we have acetate, which it's kind of helpful to learn that pattern there. That's acetic acid. It's not super on the test, but it's just like one more little bonus, maybe one more familiar thing so you don't get confused or worried, like, what's that giant thing? And with this H on the end, what they mean is that's the acidic H that's kind of on offer to whatever's willing to take it. And this one's fairly willing to take it. So could this H travel to there? Yeah, it could happen genuinely, really, to a noticeable amount, in which case you'd get this. 5 is almost an intro level set of problems. It's almost not worth talking about. Classic acid and classic base. They aren't strong acids and bases, but you have an OH minus type base, I mean, because remember with that ammonia, remember not all bases have OH minus in them, but this one does. And so what we tell the intro kids is, acid and base make water and a salt of the remaining ions. Sure, and just make the charges add to 0 and balance it left and right. And that's what we get here. And then on this one, that's what we get here, except I will point out that you can write these together, and this is the salt of the remaining ions after you make the water. But assuming this is in water, how else did they meet? That's not going to happen. That's a super soluble. That's a super soluble, the sodium. You can write this all day long, but it doesn't mean it's going to really work. That Na is never going to attach to that in water. So we can write this, but since we know that's aqueous, these aren't actually attached. So on this molecule, what you're kind of expected to recognize is that, again, we have 3 covalent bonds on nitrogen, which means we have an unbonded pair, which is a good landing site or bonding pair for an H+ that might be on offer. So if this thing was going to act as a base, where would it act as a base? Well, that is definitely the spot that it would like to act as a base on. And so, okay, here it did. And then we've added a proton and no new electrons because it used its own electrons. And so the whole thing turns positive. Now, I will also point out that this won't exactly be tested, but it might be helpful to recognize that this is called a carboxylic acid. They won't ask us naming. They have dropped all the organic chemistry stuff like naming and so forth from the test years ago. But it turns out, just in case this helps, that the electronegativities of these atoms pull these bonding electrons this way, which means this H is weakly held, and it's kind of, in a metaphorical sense, kind of hanging on by its fingernails, and it's on offer. Somebody want to pick this thing up? And there are plenty of things that kind of do want to pick that up. And so if that happened, that's what we would get there. On 7, we want to talk about something slightly different, whether the solution made by dissolving these, to whatever extent they're willing to dissolve, be acidic or basic once you get done dissolving them. So we know that ionic pairs, plus minus pairs, dissociate. They break apart into the separate ions when they dissolve. So if I dissolve this, and boy, is it going to dissolve with ammonium on it, right? You got to know your super solubles. When it dissolves, we're going to get these split up. So what would we get? What situation would we get? So can you create Cl- attracting H+ and have it actually stick? No, because that is a strong acid, and your chances of forming a strong acid in water are at 0. Forget it. It's not going to happen. And you have to know your list of strong acids and bases. They think you know that. Go look at it every day or something until you just think it's pointless because you already know it. Now, if you put this in water, what have we said about 3 times already just in this video? That has a chance of running backward and donating one of the H's. And so if it did that, we would get this. And there's the plus there. Before you think, oh no, he cheated, there's the plus, the H+. And so if it carries away the plus characteristic, then this is neutral. Now I want to point something else out. Really what it is it's the ammonium plus the water. And where did the H go? Really, the H that left here went onto the water, and really what you get is this, called a hydronium. Notice that's a water with an extra H, and we gave it an H+, so now it's positive. However, everybody cheats. It's just a lot more writing, and you get all the same math answers almost always. I mean, I don't even know, with an acid situation, I'm not even sure it's ever worth it. So everybody cheats and just pretends the H pluses are running around alone. They're not. It's ammonium, but even the AP test doesn't make a big deal about it because you do get the right answers. So, I mean, everyone cheats it. When these split up, and boy, is that going to split up, that's two super solubles. Can you attach an OH minus to that positive? Nope, because that would be forming a strong base in water. Not going to happen. Can you attach an H plus to that in water? No, because that's forming a strong acid in water. Not going to happen. So the preceding neutral water to which you added this does what? Nothing. Nothing attaches to anything, and the water is not changed. If it was neutral, it remains neutral. You don't affect the pH with a double super soluble like this because nothing sticks to it. So the acid-base nature of the water is not affected by that. So you put these in. Is sodium going to attract something? Nope. Could carbonate attract something? Yeah, it could attract something. There's an H stuck to it. In which case, now let's follow this. You've attracted an H plus out of it. That makes the acidic nature of the water less because you've removed some H plus by being a base, right? This is a base. And if you remove H pluses, does the water get more acid? No, you just used up some of its acid character. It becomes more basic. It becomes more basic. And then really, since we're talking usually in the trillion kind of numbers here, and actually that may not even be a joke at all. In fact, sometimes that's really low. There's always one more. And so if you put one more on there, we talked about this before, give it one more H, and you have the opportunity to do a little rearranging and form two of our favorite stable chemicals. So you're actually fairly likely to create that. D gets tricky. Let's consider the Br first. Can you stick an H on Br in water? No, because that's forming a strong acid. That's not going to happen. And the thing that's really easy to forget is that we're not going to talk about so much, can this attract an OH minus, but you know what we keep saying? That is an N with 3 H's, and then it's bonded backward, well, to the carbon, we assume. It can't be bonded to the H's. And we have an N with 4 covalent bonds, and 3 of them are H's, and that has a habit of giving up one of the H's. That's going to be slightly acidic, and so could something, maybe even water, come along and snatch an H off it? Yeah, it could. And again, if it's only in water, then it's really water plus, and then this is H3O plus like we talked about back here, but everybody cheats, so let's skip it. And this acted as an acid to whatever. Now, if it's only in water, then what we did was we donated this to water, and the acid nature of water went up because this has more H pluses running around to give to, well, whatever the next thing is that comes along. So the water becomes more acid when this happens. These split up. Can you form lithium hydroxide? Nope, that's a strong base. Could this form? Sure, to some extent. How much? Well, you got to go look at the Ka, and we mean Ka like that. Right, that is the constant for the reaction, and A just means being an acid. There's also Kb for if you're talking about being a base. These split up. You can't form this because it's a strong base. Could this attract an H? Sure, in fact, that's acetic acid. So is acetic acid a thing that exists? Yeah, even in water? Yeah. Could you form rubidium oxide? No, that's a strong base. Could this attract H? No, because you would be forming a strong acid in water. Know your list of strong acids and bases, and that's not possible no matter how many times we write it. 8 requires some actual thinking, but they do think you can do this on a multiple choice test if you calm down and really put your brain in gear. A is not so hard. B and C require some actual thinking. So hit pause and have a think and go ask your teacher questions or something later if you still need it. So without using a calculator, determine the whole number pH. So this one is super easy because you can just do it with a pencil, because we know that pH and pOH have to add to 14. So if I have one of them, they just tell me pOH is this. Okay, I'll just subtract out and I'll get pH here. 14 minus this one gives you that one. Whichever one you have, you can just subtract out of 14 and it gives you the other one. So this one is just easy. You probably don't even need a pencil, and you can say, oh yeah, it's between 9 and 10, and you choose the right bubble. Now in B, you have to actually know what you're doing. And then you get kids saying, I can't take negative log of that in my head, but you don't really have to. Let's just simplify it. Let's say, just what if it was 1 times 10 to the negative 8 molarity? What would the pH be then? It'd be 8. But this is a little stronger in H plus character, so it's a little more acid than we just said. And remember, acid goes down the pH scale, so it's not 8, it's a little down from 8. It doesn't reach 7, but it's between 7 and 8. On this one, and this gets extra tricky, they give us the OH minus molarity. And I can't do negative log of this in my head. Okay, but let's just pretend it was 1 E negative 1. What would the POH be then? It'd be 1. Okay, so then in that case, what would pH be? 14 minus 1 would be 13, pH, right. But this was a little stronger in the basic character than we said. It wasn't 1, it was 4.1. So when we got this POH, we know it's false. Which way do we move? This is a little bit more basic than we were talking about. So the pH isn't 13, it's farther up the pH scale. It's more toward the basic end than we just said, so it's between 13 and 14. 9 is a question they would never ask you on the real test, but anyway, so the KW depends on the temperature, and it's only 1 E negative 14 at 25 degrees Celsius, and they're saying it's 0 degrees Celsius. So they kind of cheated, and it's not 25 degrees. And that really does change KW, and it changes the pH of pure water. The pH of neutral, pure water is not 7 at 0 degrees Celsius. They're telling me the pH of pure water is 7.47. Okay, all right. So what's KW? Well, remember, KW will be the value of this times the value of that, and we know they're the same number. So it will be this times itself squared, and that gives me KW here for only at 0 degrees Celsius, not at 25 degrees C. And we won't work with that on the real test, so this is more just a mental exercise. On 10, you may understand this already, but it's maybe good at this point to review. What do we mean by a neutral situation, a neutral solution? It's where these values are equal, and therefore the ratio to them is 1 to 1. In an acidic solution, we have more H plus than OH minus, and so this ratio as expressed here would be greater than 1. In a basic solution, we have more OH minus than H plus, and therefore this ratio, if you divide out, is less than 1. On B, they want to talk about 40 degrees water. Oh, sure. So the KW is this. If you say so, they will put in a strong acid, and we just cross out the Cl because that's not going to affect anything about the pH values or the acidic or basic nature of the water at all. So I'm just going to say that this is the molarity of the H plus because that I care about. You can just borrow this number as the H plus molarity off a strong acid. So what's the OH minus molarity, brackets means molarity at 25 degrees C? Well, this times that has to be KW. So therefore, if you know one of them, you can divide KW by that one and get the other one. Let me get this. Now, it's the same math at 40 degrees Celsius, except that KW changes. And so we divided into a different number, we get a different answer, and it's this. So C asks, has this become more or less acidic or remained unchanged? Well, the OH molarity went up by over double, which admittedly on these scales is not that much because we're used to dealing in things like it went up by a factor of 10,000 or something. So double, honestly, you could hardly even tell, but it did change. It did get bigger just from the temperature rising, right? The temperature rising. So it did get bigger. So is this a more acidic, less, or what? If the OH minus went up, that's a more basic solution. That's less acidic. Or to say it another way, as this gets produced more and more, what does it do to the H plus available in the water? It reacts with it and makes water. So what's happening to the acidic character, the H plus character of the water? It's going down as that stuff meets up this and forms pure water, H2O. Either way you look at it, the acidic nature is going down when this number is increased compared to that, or the basic characteristic is going up. And I'm going to further ask you, so what's the pH doing? Take a moment. If it's becoming less acidic, the pH is going up. And I do think you know that, and that needs to be in your hip pocket ready.